Hello, class. Honestly, not so well personally, but hopefully all will be remedied in a few hours. Let's just say it involves the doctor, and they're really slow, and they didn't finish in time, so I ran over here, and I don't know yet. So I'm apprehensive. How about you? Well, I see, who's got a long weekend ahead? Who's traveling? Anybody? You're like, what are you talking about? Monday's a holiday. Don't come to class. I won't be here. Okay. Get that out of the way. Logistics. If you didn't notice, like I have to walk around here to look at it. I have posted yesterday your first real assignment. One where you have to actually answer questions that I hope you can figure out. So it's on WebAssign. There's questions from chapters 1, 2, and 3, and it's currently due 11:59. Right before midnight next Wednesday. There's only 15 questions. Most of them are multiple choice. There are some short answers, like it would ask you blah, 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 yes or no. You put yes or no, and then there's a box where you can write out, because it wants you to explain yourself, explain why you're saying yes, and that's where actually more points will be. You'll get 1 point for answering yes or no right, And I did figure out how to grade these things, that's why I posted it. So currently I have on the multiple choice, if there's more than 2 answers, let's start with it. If there's 2 answers, yes or no, you get 1 submission. You'll know as soon as you submit it whether it's right or wrong. You get 1 try. Sorry. If there's 3 answers, I give you another submission. So you could get the first one wrong. It will tell you, so you know it's one of these 2. You can answer again and get half more points. I'm deducting 50% of however many points are available, and it says by the question how many points there are. So that way you'll know what the right answer is. You can still get something other than 0. I would love that as a student, so there you go. If it's an essay or a number, where it's just asking for a number, because you need to do some minor calculation, and they're minor this time, you get some multiple submissions too, but again 50% off each time. If it's the essay, finally get to it, those I currently have worth 2 points, because if you just put an X in there, WebAssign, I probably shouldn't tell you this. If you put an X in there, WebAssign thinks I got it right. And it'll tell you got full points for that essay. Don't be confused. We're going to go grade every essay and read them and adjust the points accordingly. So if all you put is blah, 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 we'll give you 0 points for that essay question. That's where you'll explain yourself and whatnot. I'm thinking I'll give you 1 point for I can tell you sincerely tried to answer the question, but you're wrong, and 2 points if you got it right. Or, a lot of people put things in there, but you're using the wrong terms. Well, you said velocity, but it's really acceleration. I think I could tell what you meant, so I'll give you a point. That's where we get to go back and grade them by hand. Next Wednesday night. So we'll get through another lecture. If for some reason I get bogged down, or you all look at it and spaz, well, I might be swayed, but that's what I'm doing for now. All right. Last time I ended with this demo, and it was I used it to show which concept? Very good. All right. However, what I really wanted to do, raise your hand if you've never done this before and always wanted to try, but you were chicken. Today's the day. Come on down. Because there's lots of things where I want to try to do it, but like I said, if I think I might break it or mess it up, I'm usually tentative. So we'll walk you through it. Go ahead and pick up the end and scrunch it up. Yeah, I would kind of... Yeah, all right. You want to keep it smooth. So you guys can all try this at home. Pointer number 1. If you bring your hands now up to here, go ahead. See how it's saggy there? That's good. We're going to get to this in the next chapter, chapter 2. he's going to start pulling, but that way he's up to a faster speed before it actually starts sliding. If you were to back up and make it taut, start pulling from there, it has to start from 0 when it starts pulling on this. So if he starts up close, you can get up to a faster speed, because the key here is to get it out fast enough before friction comes into play and overcomes its inertia. It wants to stay at rest. Things at rest want to stay at rest. They tend not to want to change their motion unless, what? They're acted upon by a force, which is this sheet trying to pull on it. So if you can do it quick enough, that's the key point, going fast. So that's what you get to do. Point number 2. We want it to slide out from underneath it, not exert a force upward and lift it off the table. So make sure you pull down. A lot of people want to just yank straight out, and unintentionally they pull up a little bit and lift the plate up or something. So we'll have you go down. And then the less assuming tip, if you want to try this at home, cut the seam off the cloth. It's really annoying. If you leave the seam on and it tries to slide underneath, what's it impart to the plate?
Grabs it.
Yeah, it grabs it. I heard friction. And which way do you think it pushes it? It's like a speed bump. Up. We don't want it going up, so that's why you get rid of the seam. Are you ready?
Yes.
Okay, give him a drum roll. Hey! Piece of cake. And that's your first time ever?
Yep.
See, all right. And I didn't pay you ahead of time? Well, a plant, yeah. Now, observations. Good scientist makes observation. What did you notice about the objects? Anything? Their motion as he pulled it. Anything you noticed? Obvious or not? It scooted a little, yeah. Yeah. If we went faster, it'd scoot less. You go slower, it'd scoot more. Yeah, it still moved a little. What else?
If you did it with an empty glass, would it change the reaction?
Okay, what do you think? I'll think of some answers. If the glass was empty, do you think the glass would still stay put? Move more, move less? Those are your options. And just because I want to try this and you're still working on your clickers, pulling's open. A moves less. B moves more. C doesn't matter. A less moves less. Without the water, it moves less. A. B moves more. C doesn't matter. It's channel 44. I've gotten 20 responses. A, with less water, A, it will move less. B, move more. C, doesn't matter. It's probably most people. Anybody not voted? Going once? Going twice? Sold. Okay, I could see the results. B was 51%. B was move more. Okay, somebody that thought it would, well, no, I'm going to do it this way. B, most people thought, just over half of you, about half, thought it would move more. Next biggest answer, about a third of you thought it wouldn't matter at all. So now talk to your neighbor and try to convince them of your reasoning, and we'll vote again in a minute. All right, polling's open. you can start putting in your answers and discussing. A moves less, B moves more, C doesn't matter. Let's see who convinced whom. If anybody changed their mind. A moves less, B moves more, C doesn't matter. Or keep talking if you're not sure. I'm keeping track of all of them, but I'm probably not counting yet because I have empathy this week. Don't worry.
I had my medal together.
Okay. Yeah. I figured I needed a grace period, so. Not as many responses yet as before, so we'll wait a little longer. I know there's at least 5 more of you out there. Okay. Anybody else want to vote? Change your mind? Going once? Twice? Oh, there's more people voting this time. That's good. All right, and the results are cool. Now we have 43% of you, less of you, thinking that it'll move more. And more of you think it won't matter. So the people that didn't think it'll matter swayed more of those that do. So, somebody that thinks it will move more, you want to explain yourself?
Well, it's just inertia is proportional to the amount of mass.
Okay.
It's a property of matter.
Okay, and it has less mass
And
without
so if it has
less
less
water.
mass, I figured that it will have less force keeping it in place. So I think it'll move at least a little bit.
Okay, good. And now someone that thinks it doesn't matter.
Actually, I thought was that because there'll be more water, there'll be less water, there'll be less weight. Less weight means less friction. But in that particular case, I don't think it matters at all because it's such a small movement, so it doesn't matter.
Aha. You know what? I shouldn't have folded this up. This is busy work, right? Let's do it again. And I'm going to make it more obvious. Let's see. Let's do, just so it's more conspicuous. We'll keep the glass full. And you convinced this is a lot less mass? This will be like the glass with less fluid. Does that seem fair? That bugged somebody that's not consistent. All right. And here we go. Comparisons between how the two moved. The spoon moved more? And that is correct. The less massive something is, the more it tended to move. And that occurred the last time I did it and when he did it. The silverware, you could hear moving, where the plate in this seemed not to move as much. And it's because they have more mass, which does mean they have more inertia, which does mean they have more resistance to change of their motion. And in this case, they started at rest, so they are less likely to want to move, and thus harder to get moving. You are right, sir, that there is less friction on it, though, if it's lighter. So you are correct with that. But, so something that has less mass has less inertia, and it's easier for the same force to make it move.
Okay, so the inertia thing is more important than less friction.
In this case, yes. Yeah. And welcome to the world of physics where you can't separate one thing usually. There's always multiple things going on, it seems like.
So how would you, I mean, that's just always true, that the inertia
Yes.
is,
This is also in part, obviously, that example is a little hard to see the spoon move further, but isn't in part because the contact the spoon has to the table or the block. Because it's only contact that has 7 points.
Yeah, good. We're going to get into friction, and he's wondering if the contact area matters. And actually, well, friction is one of those things that seems simple in physics, and I won't lie, physicists still don't fully understand it. And the equation they give students is an approximation, And for most things we deal with in our life, contact area does not affect friction. And I know it's ahead of it, but who cares? You guys are smart. You can figure it out. Bad example because I can't tip it over. Hold on. Let's grab this. All right. Try to slide it around. It's 26-pound lead brick. There's a certain amount of friction. If I flip it up on here, yeah, there's a tendency to think, oh, there's less friction now because it's less contact. Two things have changed, though. There's less surface area, so there's less spots for it, too. So that's why I would logically think there's less friction. But the pressure is increased. We haven't got to that. The weight is the same. The mass is the same. So it's being pulled down with the same force. But it's over a smaller area, so it exerts a greater pressure. So you can think of this bigger area, more contact points, but it's spread out. So each one feels less force. Here, there's less contact points, but each one's feeling more. And you know this. Would you rather get stepped on by somebody wearing high heels or a snowshoe? It's that concept. So the hand-waving answer is they balance each other. And contact area does not affect friction. And I was going to teach you that later, so learn it now.
What about the thickness and texture of the cloth?
Oh yeah, that matters too, sure. Yeah, because running something over sandpaper is different than running it over Teflon. Yes, that will affect friction. So there are multiple things going on here, and I am generalizing. But it's safe for you to know and learn that the more massive something is, the more inertia it has, and the more it wants to resist a change in motion. And that's whether it's at rest or already moving. That's the key point here. So practically, the heavier your table setting, the more likely you are to succeed at this. So you try this with a styrofoam plate, you won't impress anybody. And I've been to DI a few times. This isn't the first plate. Okay. So, if you haven't caught on, you need to know inertia, and you need to know Newton's first law, which I've been stating, but if you haven't made the connection, Newton's first law is, and it's in your book, bold-faced, you don't need. Things at rest want to stay at rest, and things in motion want to stay in motion, and unless the force acts upon it to change that motion. Inertia is a resistance to change. That's Newton's first law. And it seems simple until people think like we did. What do I have here? This little hover puck. You can push it, give it a force to get it moving. But once it's moving, it has this property called inertia. And it'll just stay moving until some other force acts on it. This reduces the friction so it doesn't slow down like you normally would expect. But once it hits the wall, boom, that exerts a force on it, changes its motion. Changes motion. Changes motion. And if I go slow enough, what changed its motion this time? It is friction. This isn't frictionless, it's just a lot less friction. And you can tell that by if I turn the air off. Lame. So it would keep moving forever at a constant speed until some other force acts on it. Yeah, it seems to just zip along, but it's because we're used to, subconsciously we expect things to slow down. Now you know why, because there's a force acting on it, for friction usually. Yeah. Over here. Okay. You guys know what it is, but we'll define it anyway. Force. We've been saying what force is, but if you had to actually define it, we're in physics, so we're going to. Simple. A push or pull. That's one easy way to think of it, especially in reality. That covers 98% of everything, right? Your book says any influence that tends to change the motion of an object. And I hope that makes sense to you now, because it's just going to keep doing its thing unless you act on it to influence its change in motion. We're going to learn later, I'll tell you now, that a change in motion is an acceleration. We'll get to that. What's more, let's do this. I drop this piece of paper. Well, as soon as I let go of it, what force acts on it? Actually, before I let go of it, it's acting on it too. So we'll just start right here. We know gravity is acting on it. Anything else? Yeah, my hand. Gravity's down. My hand's up, pushing up. And so there's two forces on it. We're going to define the term net force. What do you think the net force in this case is? Right, it's summing all the forces up. And your book gives you that fun symbol if you've never seen it before. Net force. And they will do this symbol. And it's a Greek character sigma. It means summation. And it just means you can sum up all the forces. So if you have F1 plus F2 plus F3 plus whatever. And let's say F1 is gravity going down. F2 is my hand pushing up. We would give them different signs. One would be positive, one would be negative. So how do you think the magnitude, the amount of force compares? Force of gravity and the force of my hand? Yeah, they're equal. The force up equals the force down. So a plus F plus a negative F, they cancel out. You get 0. We're going to get to it too. But you guys are smart. Magnitude, it tells you just the number. You know, if I say force is 100 newtons. Newton is a unit of force for the standard unit. You might be more familiar with pounds. You can convert between the two. That is its magnitude. Force is a vector, though. It always tells us which direction it's pointing. So in this case, stop holding this up. Gravity is pulling it down. So we could say it's a negative 100 newtons. The table is pushing it up, opposite direction, so we'd have to do the opposite sign, a positive 100 newtons, or 100 newtons to the north. Something that's a vector has a direction to it. Another example is the next chapter. Speed is how fast you're going. I'm going 50 miles an hour. Remember, I'm including the units. Those are important. If you just say I'm going 50, that doesn't tell me anything at all. 50 miles an hour. That's your speed. That's a scalar. That's just the magnitude, a scalar. These terms are in your book. But since they use them, and I'll be using them, you might as well know what they mean. This is only magnitude. Like 50 miles an hour or 100 newtons. Speed is a scalar. Vector gives direction also. It's both. So 50 miles an hour northeast. Now we have a velocity. Velocity is a vector. It is the speed with a direction. Speed, just the magnitude. Velocity, magnitude with direction. So velocity and force are vectors. Speed is an example of a scalar. And this all came up because we wanted to discuss net force. That's more than one force acting at a time, and it can be in different directions. And if you sum them up, that's going to determine whether the thing's changing its motion or not. Is this changing its motion? So what's its net force? Right, right. How about what's its net force? Yeah, I'll throw in an approximately. While it's moving, is it changing its motion? Because of inertia. So if it's not changing its motion, what's its net force? Whew, sorry. I didn't hear what you said because it's too noisy. What's its net force? 0, that's right. So things don't have to be setting still to not be changing their motion. We stated that already, but I can't emphasize enough. Things can be moving, but if they're moving at a constant speed, if you're in your car going 50 miles an hour, straight down the highway, are you changing your motion? 50 miles an hour straight down the highway, constant 50 miles an hour. Are you changing your motion? No, you're not. You're at a constant speed. So the net force on you is 0. Does that mean there's forces not acting on you? What would be a force acting on your car? What'd you say? Acceleration. Your motor's working, trying to propel you forward. Why don't you go faster and faster? Wind resistance. Drag. Right. We'll sum all those up as friction at the moment. So there's two forces that must be balanced at that time, creating a net force of 0. And so you're not changing your current state of motion because of your inertia.
Back to the vector, use the example of horizontal, and in the book I know it talks about left and right. Is it not used in vertical motion or vertical?
You're absolutely right. It can be. Yeah, a vector can point in any direction. It includes direction. I'm just dealing with no more.
So I think a vector is meaning a line.
Yeah. Your book explains this well. Say that's the lead brick, and here's the table. I would draw a spot on the brick and say, oh, gravity is pulling it down with force 1, let's say. And so now I'm drawing what scientists like to call a free body diagram. Yeah, you can call it a picture. I don't care. This arrow represents the force. And if you draw an arrow, well, that's already automatically implying a direction. It's a vector. Well, that's good because force is a vector. So the length of this represents the magnitude. So let's say that's a negative 100 newtons. Just throwing it out there. So if I draw some other vector on it, like the table pushing back on the block up, F2. If you draw your picture to scale, I automatically know that, this must be positive because it's in the opposite direction. And let's see, that's the same length as that, so it's positive 100 newtons. That's how vectors work, and we represent them with arrows. So they're lines, but they can go any way you want. So if I have F3 up here, excuse me, writing on top of stuff, what do you think its magnitude is, roughly? Louder. 300 newtons. Do you see a positive 300 newtons? Because it's up, and it's roughly 3 times as long. Okay, say we got F3 and F1 existing. What's the net force?
200 newtons up.
Very good. 200 newtons. You include the units and said up, because it's a vector. So, would this thing be changing its motion?
Yeah.
Yes. Yeah, it would be going faster and faster up. Don't ask me how at the moment. Maybe this is an elevator moving up. I don't know. But yeah, if you just know there's 2 forces on it, and that one's bigger than that one, he's going to win. And you get a net force changing its motion that way.
So would you say net force is a vector or uses vectors?
Net force is a vector. It's a sum of all the other forces, which are also vectors, acting on an object. Cool. Now you guys got net force. Some of these real life makes more sense. Let's do figures. Turn that on. a question. It'll come up. And let's see if you can figure this one out once it wakes up. So get your clickers out. Might as well open polling because I don't need to wait. See what you think. The author, if you've been reading the book, he used to be a painter. He had a good story about this. This is what got him into physics, actually, discussing with his co-painter. So it's suspended there, and the things on the right and the left are scales that give the reading. There's 700 newtons of tension in here, force. To hold it up right here, it has to go up with 700 newtons of force. 500 on this side to hold this end up. He weighs 600 newtons. Which way do you think that acts? Down. Good. In physics, you make lots of assumptions. They don't always spell it all out for you because weight acts down. And his bucket's 100 newtons. So what's the weight of just the scaffold, that board? Can you figure it out? Your clue is this is net forces that should sum up. Another clue as you're thinking. You don't need the answer yet. What do you think his net force is? The net force is 0. Why do you say that?
Because none of the objects are moving, so it's at equilibrium.
Could you hear that? I'm just curious if you can hear him when he talks. How much I need to repeat. Burl hopes that he's not moving. He's not falling and he's not going up. Is he changing his motion? No, he's at rest. So his net force is 0. Does that help you with an answer? Oh, yeah, I just realized. I'm a dork. You can't answer this one. I didn't give you multiple choice. Fine, it won't be clicker. What do you think the answer is? We got a 500. Any other votes? I heard some more 500s. Anything else? And we'll think it through. So we got a total of how much up? 1,200. Please raise your hand if you don't see that. Don't be embarrassed. This isn't the time to be embarrassed. 1,200 up. Good. Total down that we know of? 700. Right. So if they're supposed to be balanced, we're missing how much? 500. Right. So 500 newtons down is the weight of the scaffold. Does that make sense? Great. That's your answer. Let's see what you think on this one. Again, not a clicker. Say this gun shoots a ball into this tube or track and it goes around in a circle. When it comes out, I guess you can actually do this one. What the heck? Click away. A, B, or C. Which path do you think it'll take when it gets out of the tube? Get back to some inertia. That's your clue. Oh, I have to open polling. Okay, now polling opens. Sorry. A, B, or C. Let's see what you think. Oh, you guys are fast now. All right. Ooh, I'm getting more than voted before. Anybody else want to vote before I close? Okay. Most of you thought B. And a few of you thought A. Let's go back and look. B and A. This is a tough one for even for science people sometimes. Somebody that thought B, tell me why.
Well, I just thought about like my nephew's toy. He puts a car on like the little loop that goes down. The car always just comes out straight.
There you go. See, I love that. You guys are natural scientists and have made observations all your lives. He said he is your brother? Nephew has a toy. He's seen this, so he has some intuition about it already. All right. Anybody else on that one then? Maybe with a physics explanation.
Well, my explanation was that there is no force that the ball should go in the A path, so it has to be traveling in a straight line.
She said there's no force once it leaves, forcing it to take the A path, so she's claiming B. Now somebody that thought A.
Well, it just looks like it's slightly curved at the end, and so it doesn't look straight down to me.
And that's in reality, it probably could be true. Could be true. That wouldn't affect the result. It'll curve whether it's not, or, if it wants to curve. That's what I'm getting at. Do you want to add something?
This same process as object moving in space without any fluid in the ball moving capacity would have no resistance, therefore would travel in a straight line in the direction once it's stopped being exerted from the force.
Could you hear that? B is the right answer. And for the reasons that War stated. Inertia. Once it leaves the tube, it can't act on it. It can't push on it from the sides. And so it will continue in that direction because of inertia. So it will go straight. You can try it out. Get a little thing, throw a ball around, let it come out, or put it in a tube, get a toy, and observe it. I can pull something out next time if I remember. It's tempting, though, to think A, because, it's been curving, it'll just keep curving. That's not a natural tendency. Just remember what forced it to curve while it was in the tube. The tube. The ball always wanted to go straight until it ran into the tube, and the tube exerted a force on it and said, nope, go that way. Okay, straight. Nope, that way, straight. And it's the same in your car. When you turn a corner, you're going this way. And all of a sudden you go, and I turn that way. Which way does your body want to go? Straight. What gets in the way? The car door or your seat belt coming around, pushing on you, saying, no, go back that way. That's why we wear seat belts. Yeah.
I have a question. Depending on the fact that this whole example has no definition of friction based upon it's not slowing the ball down, wouldn't that even classify actually intensify the speed of the ball because it may have a rotation of its desired path?
Excellent question. Excellent question. And that's chapter 3. So,
Could you repeat it?
yeah. 1, 2. That is 3. I'm getting them mixed up. Chapter 3 is on linear motion with speed, velocity, and acceleration. That's where we're starting to overlap them now. He said, there doesn't seem to be much friction here. Let's say there isn't any at all. The ball, maybe it should speed up because every time the tube pushes on it, that should act on it, right, to change its motion. And that's very logical. It won't, though. And that's because velocity is a vector. There's 3 ways to change motion. And we'll go ahead and say acceleration is a change in velocity. Let me give you that first. And you guys are bright, we'll just give it to you. Acceleration is what we call this change in motion. I've been using the word motion, but it's a little vague. Usually, more specifically, when I say motion, I mean the velocity. This is another Greek term, delta. It means change in. So this is our first equation. And see how this is shorthand? You don't have to write this out every time. This reminds me that acceleration is a change in velocity, and that takes a certain amount of time. A change in velocity over time. And if you know your algebra, if you multiply both sides by time, let's multiply both sides by t, that way it keeps it equal. Then the t moves over here, and it cancels on that side, And you can see it another way if it helps you. A change in velocity, in order to make something change its motion, you have to accelerate it for some amount of time, because it'll take time. Can't do it, poof. So, back to your question. There's 3 ways to accelerate something, change its motion. You can speed it up. That's what we're usually thinking about. Let's relate with a car. Push the accelerator down, and you accelerate. You change your velocity. I'm now going 50 miles an hour. Now I'm going 100. You change your velocity. Another way? Slow down. Hit the other pedal, the brake. A deceleration is like a negative acceleration. You're still accelerating, just in the other way. Notice this, though. Your car is still going forward, isn't it? And you can accelerate the other way. That slows you down. You follow that? Some people get confused with that. You can still be moving this way, but be accelerating that way. Give me another example.
So it'd be like if you're landing an airplane, the airplane is going to slow down and your body's going to slow down with it.
Yeah. It's still moving forward, let's say the positive direction, but you're accelerating negatively, slowing down. Right. Another example? Yeah, a ball slowing down. Yeah. This is safe. Which way is this accelerating right now? Wait. Bad example. Let's just simplify. Which way did it accelerate? Was it increasing its speed or decreasing? All right. How about during that trip?
Still accelerating, decelerating.
What's pulling it down? Which way does gravity act? So it was accelerating down the whole time, even while it was moving up. That's changed its motion, caused it to stop moving, made its velocity 0. And then it increased speed coming back down. Does that make sense?
Kind of like a roller coaster.
Exactly like a roller. Man, amusement park. Go to next time you're at Lagoon, man. You guys, I hope, remember this class because it's just full of all this stuff. That's actually the point of an amusement park. Oh yeah, who cares? A bad amusement park ignores physics. A good roller coaster that doesn't change its motion is not a good roller coaster. You want it to change its motion. Speed up, slow down, and the third. Very good. Velocity is a vector. So if you change velocity, one way to do that is you do not have to change the speed. You can change the direction. So I'm going the same speed. Do you agree? Look like a dork. But am I accelerating though?
Yes.
Technically I am because I'm constantly changing my direction. Let's go back to the marble and the bullet in the tube. What's constantly causing that change in direction? The force of the tube. Yeah. And it takes a force to change direction. Didn't necessarily speed it up or slow it down, but it still was a force causing an acceleration, which is a change in motion. Hey, see, you guys are smarter now than probably most of the population, because most people don't get this.
So an object can accelerate without changing its speed?
Yes, repeat that.
An object can accelerate without changing its speed?
Absolutely. And how?
Changing direction.
By changing direction. So things going in a circle at constant speed are accelerating. When you're on the merry-go-round or the Ferris wheel, you are accelerating. Something's constantly pushing you inward. We call that centripetal force. Some of you have heard of it. Maybe you've heard of centrifugal force. I don't want to get into it at the moment. But that's like the car. Inertia wants to keep you going straight, not change your motion, right? Until something acts on you. The car door to push you. So it takes a force to change your direction, your velocity, and thus you're being accelerated around in a circle. Doesn't mean you're speeding up or slowing down, but changing velocity, direction. Well, let's see, we got 4 minutes. Let's just do a few more of these inertia demos and call it good. Give you a few things to have a fun with at the long weekend. Here's a card. Place it on top. Little flat spot on this ball. Put it over the cup. And this is designed, I can flick this spring, and it's like the sheet. If I can do it quick enough, the ball has inertia. And the ball does not get moved. Its inertia keeps it in place. Let's do this one. All right, come pull it out from underneath real fast, will you? It's the same game. We'll give you another try.
Sorry.
Try it on this side. All right, do it again.
Oh, sorry.
That's okay. That's all right. Come here. My physics teaches me that if I went fast enough, I ought to be able to do this. So here's your little trick. How can we pull this out faster? Grab it here and karate chop it. Get where I'm at. Again, see, it's bent, so by the time it starts moving, it'll be going faster in the first place. Yeah! All right, next time you're at a restaurant, or not, you can bet your friend, do this game. You think you can pull it out? You can say, well, if you can, without knocking the bottles over, you can have the dollar bill. The hardest part is balancing this thing in the first place. Do your karate chop, right? Hey, I get the dollar. All right. Who doesn't like me already? Thank you. Will you help me out since you're just over here? 26-pound lead brick. Can you aim? Just hit the brick. Not the table, not me. Go ahead, tap it. Yeah. Harder. Harder. As hard as you want. Hey, you almost missed.
You were almost.
Hey, you want to try it?
No, why not? It's not like I need my hands for anything.
Here, you do it yourself. You'll trust you. Harder!
I would, but it's a bit more difficult than
Why am I not, flat? Thank you very much. The thing that hurts the most is the fact that this is 26 pounds. It just hurts resting on your hand. Ow! Just dropped it on my thumb. Hitting it, though... Ow. Hitting it actually doesn't add much to it at all. I hardly feel the hit. I can tell he hit, yeah, but... This has so much mass. It's got a lot more inertia than we're used to. And so, when he hits the brick, it exerts a force on it, trying to make it move, right? It wants to go down. Well, it resists that change in motion. It tries to stay put, just like everything else. And so it does not go down as fast as the hammerhead itself is. And so the hit hardly hurt at all. One more. And we'll all finish. This is fast. This is you in your car. You're moving along with your car, right? You hit a wall. And inertia says, I don't want to change my motion. You keep going forward. Do it again. See, it moves with it until you stop. If you're not belted in, then you go through the windshield. Or, if you accelerate too fast, you're at rest. You want to stay put. That's why you feel like, whoa, slammed into the back of your seat. It's inertia. So go observe inertia this weekend and start working on the homework. And have a good weekend. Yeah.